Dear children, so you must have all been familiar about sound and how the sound is produced. Look at the objects which are producing sound. So let's start off with the chapter. Yes. Now let's move to the chapter sound. Sound. If you have never done this, then do it and observe of the stretched strings. You will get sound. Here is a small activity, kids. Just look around your place in your house regarding the musical instruments. Then let us discuss about which instruments and how the sound is produced. In most cases, or in almost all the cases, there is a vibration which produces sound. So we have to understand vibration or oscillation will create sound. These are the old instruments you can see, like veena, violin, sarang, etc. Now let's understand the propagation of sound. Sound is produced by vibrating objects. The matter or the substance through which the sound is transmitted is called the medium. It can be solid, liquid, gas. Sound moves through a medium from the point of generation to the listener. When the object vibrates, it sets the particles of the medium around it vibrating. The particles do not travel all the way from vibrating object to the ear. The particle of the medium in contact with the vibrating object is the first displaced from its equilibrium position. It then exerts a force on the adjacent particle, and as a result of which the adjacent particles gets displaced from the position of rest. After displacing the adjacent particle, the first particle comes back to its original position. This process in the medium till the sound reaches your ear. The disturbance created by a sound of a source of the sound in the just look at these two images. You have the prongs, and when the prong is on the top, and when the vibrating tuning fork, when we vibrate the tongue, the sound waves goes into the water from the air medium to the liquid medium and then to the glass medium. So it propagates through air, water, and also the tumbler. Then here is another one where you have a direct contact of vibrating fork with the water. So the level of vibration transmitted to the water can be observed here. From the above activities, what can we conclude? Can you produce sound without a vibrating body? No, we need vibration to produce a sound. In above activities, we have produced sound by striking, tuning fork. We can also produce sound by plucking, scratching, rubbing, blowing, or shaking different objects. As per the above activities, what do we do with the objects when we set the objects vibrating and produce the sound? Vibration means a kind of rapid to and fro motion of an object. The sound of the human ear is produced due to the vibration of the vocal cords. When a bird flaps its wing, you can hear any sound. Think how amazing the buzzing sound accompanied by the bee is produced. Here is a picture. A beam of light from the source is made to fall on a mirror. The reflected light is falling on the wall. Can sound make light spot dance? Take a tin, remove the both ends, make it into a hollow cylinder, take a balloon, stretch it over the can and wrap the rubber band around the balloon. Take a small piece and mirror, use a drop of glue to stick the piece of mirror to the balloon. Allow the light to a slit to fall on the mirror. After reflection, the light spot is seen on the wall, as shown in the figure. Talk or shout directly into the open end of the can and observe the dancing light spot on the wall. Discuss with your friends what makes light spot dance. Can sound make a light spot dance? Take a tin can, remove both ends to make it a hollow cylinder. Take a balloon and stretch it over the can. Then wrap a rubber band around the balloon. Take a small piece of mirror. Use a drop of glue to stick the piece of mirror to the balloon. Allow the light to fall on the slit, and after the reflection, the light spot is seen on the wall as shown in the figure. Talk or shout directly into the open end of the can and observe the dancing light spot on the wall. Discuss with your friends what makes the light spot dance. The medium travels through the medium and not the particles of the medium. A wave is a disturbance that moves through a medium when the particles of the medium set neighboring particles into motion. They in turn produce similar motion. Disturbances is carried forward. This is what happens. Propagation of sound in a medium. Hence, sound can be visualized as a wave. Sound waves can be categorized by the motion of the particles in the medium and are called mechanical waves. Air is the most common medium in which sound travels. When a vibrating object moves forward, it pushes and compresses the air in front of it, creating a region of high pressure. This region is called a compression, as shown in the figure 12.5. This compression starts to move away from the vibrating object. When the vibrating object moves backwards, it creates a region of low pressure called refraction, as shown in the figure 12.5. A vibrating object creating a series of compressions and rarefactions in the medium. Object moves back and forth rapidly, and the compressions and refractions are created, and these make propagate through the medium. Compression is the region of high pressure, refraction is the region of low pressure. Pressure is related to the number of particles of the medium in a given volume. More density of the particles in the medium gives you more pressure and vice versa. Thus, propagation of sound can be visualized as a propagation of density variations or pressure variations in the medium. Question to all: how does the sound produced by a vibrating object in a medium reach your ear? Sound needs a medium to travel. Sound is a mechanical wave. and needs a medium like air, water, steel, etc. for its propagation. It cannot travel through vacuum, which can be demonstrated by the following experiment. Take an electric bell and an airtight glass bell jar. The electrical bell is suspended inside the airtight bell jar. The bell jar is connected to a vacuum pump as shown in the figure 12.6. If you press the switch, you will be able to hear the bell. Now start the vacuum pump. When the air in the jar is pumped out, gradually the sound becomes fainter, although the same current is passed through the bell. After some time, when less air is left inside the bell jar, you will hear a very feeble sound. What will happen if the air is removed completely? Will you still be able to hear the sound? The bell jar experiment shows sound cannot travel in the vacuum. In these waves, individual particles of the medium move in a direction parallel to the direction of the propagation of the disturbance. The particles do not move from one place to another, but they simply oscillate back and forth about their position of the rest. This is exactly how sound wave propagates. And sound waves or longitudinal waves. There are also another type of wave called transverse wave. In a transverse wave, particles do not oscillate along the line of wave propagation, but oscillate up and down, but their mean position as the wave travels. Characteristics of a sound. We can describe a sound wave by its frequency, amplitude, and speed. A sound wave in a graphic form is shown in the figure 12.8, which represents how density and pressure change can the sound wave moves in the medium. The density as well as the pressure of the medium at a given time varies with distance above and below the average value of density and pressure. Thus, a transverse wave is one in which the individual particles of the medium move about their mean positions in a direction perpendicular to the direction of the wave propagation. Light is a transverse wave, but for light, the oscillations are not of the medium particles or their pressure and density. It is not a mechanical wave. You will come to know about transverse waves in the higher classes. See, the following figure represents density and pressure of variations, respectively as sound wave propagates in a medium. Compressions and are represented, and also peaks are represented, rarefactions are represented in the below. A few questions for you children. Explain how sound is produced by the school bell. Why are the sound waves called mechanical waves? Suppose you and your friend are in the moon. Will you be able to hear any sound by your friend? Sound waves or longitudinal waves. Take a stringy, ask your friend to hold one hand, you hold the other hand. Now stretch the stringy as shown in the picture. Then give a sharp push towards your friend. What do you notice? If you move your hand, pushing and pulling the string alternatively, what do you observe? If you mark a dot on the string, you will observe the string will move back and forth parallel to the direction of propagation of the disturbance. The longitudinal veil in the stringy. The regions where the coil has been closer are called compressions, and coils where they are apart are called refractions. And you will understand that these are called longitudinal waves. Frequency. Let us know frequently an event occurs. Suppose we know that when the sound is propagated through a medium, the density of the medium oscillates between a maximum value and a minimum value. The change in density from the maximum value to the minimum value again to the maximum value makes a complete oscillation. The number of such oscillations per unit time is the frequency of the sound wave. If we can count the number of compressions or the refractions that cross per unit time, we will get the frequency of the sound wave. It is usually represented by the SI unit hertz. Time taken by two consecutive compressions and rarefactions to cross a fixed point is called as a time period of the wave. In other words, we can also, one complete oscillation in the density of the medium is also called the time period of the valley. The lower portion of the curve. The peak is called the crest and the valley is called the trough of the wave. The distance between two consecutive compressions or two consecutive refractions is the wavelength, as shown in the figure. The wavelength is usually represented by SI unit called in M. See, wavelength, trough, crest, amplitude. These are the different parts of a wave. Now let's look at the scientist, a German person who was born on 22nd February 1957 in Hamburg, Germany, and educated in the University of Berlin. He confirmed J.C. Maxwell's electromagnetic theory by its experiments. He laid the foundation for future development of radio, telephone, telegraph, even television. He also discovered the photoelectric effect, which is later explained by the Albert Einstein. The SI unit of the frequency is named as hertz in this order. Sound propagates a density or a pressure variations as shown into ABC, representing graphical density and pressure variations. A sound wave is represented by symbol T. The frequency and time period are related as follows. A violin and flute may be played both at the same time in an orchestra. Both sound travels through the same medium, that is air, and arrive at our ear at the same time. Both sounds travel at the same speed, irrespective of the source, but the sounds we receive are different. This is due to the different characteristics associated with the sound. Pitch is one of the characteristics how the brain interprets the frequency of an emitted sound and is called its pitch. The faster the vibration of the source, the higher is the frequency and higher is the pitch. Thus, a high-pitched sound corresponds to more number of compressions and more number of refractions passing through a fixed point per unit time. Objects of different sizes and conditions vibrate at different frequencies to produce sounds of different pitch. The magnitude of the maximum disturbance in the mind on either side of the mean value is called the amplitude of the wave. It is usually represented by letter A. As shown in the figure 12.8c, for sound, it's the unit will be that of a density of the pressure. Density or pressure. The loudness or softness of a sound is determined basically by its amplitude. The amplitude of the sound waves depends upon the force with which an object is made to rotate. If we strike the table lightly, we hear a soft sound because we produce sound waves of less energy or less amplitude. If we hit the table hard, then a loud sound is come. Can you tell why? The loud sound can travel a larger distance as it is associated with the higher energy. A sound wave spreads out from its source. As it moves away from the source, its amplitude as well as its loudness decreases. Now, the wave shapes of the loud and a soft sound of the same frequency. Low pitch sound has a low frequency and high pitch sound has a high frequency. Soft sound has small amplitude and louder sound has large amplitude. The quality or timbre of the sound is the characteristic which enables us distinguish one sound from another having the same pitch and loudness. The sound which is more pleasant is said to be rich of a rich quality. A sound of a single frequency is called a tone. The sound which is produced due to a mixture of several frequencies can be called a note and is pleasant to hear. Noise is an unpleasant thing to hear. Music is a pleasant to hear and of rich quality. Here are few questions, children. Which wave property determines loudness? Pitch. Yes, which sound has higher pitch, guitar or a car horn? The speed of the sound is defined as the distance which is a point on the wave, such as a compression or rarefaction, travels per unit time. We know speed is equals to distance over time. And here the wavelength of the sound is the distance traveled by the sound wave in a 1 unit time, or speed is equals to wavelength into frequency. The speed of the sound remains almost the same for all frequencies in a given medium under the same physical conditions. Example, a sound wave has a frequency of 2 kilohertz and the same wavelength of 35 centimeter. How long will you take to travel 1.5 kilometer? Given frequency 2 kilohertz, wavelength 35 centimeter, we know the speed of the wave, wavelength into frequency. After the calculations going through, please note the sound will take 2.1 second to travel a distance of 1.5 kilometers. Few questions again. What is the wavelength, frequency, time, amplitude of sound waves? In the picture, it's given clearly what is the amplitude, what is the period, what is the time period, frequency, etc. The other two are, please calculate the sound wave whose frequency is 220 hertz and the speed is 440 meters per second in a given medium. A person listening to tone 500 kilohertz sitting at a distance of 450 meter from the source of the sound. What is the time interval between successive compressions from the source? Now distinguish between loudness and the intensity of the sound. Sound propagates through a medium at a finite speed. The sound of a thunder is heard a little later than the flash of the light. So we can make out the sound travels with a speed which is much less than the speed of the light. The speed of the sound depends on the properties of the medium through which it travels. You will learn about the dependence in higher classes. This uh, you will learn about the dependence in the higher classes. The speed of the sound in a medium depends on the temperature of the medium. The speed of the sound decreases when we go from solid to gaseous state. In any medium, as we increase the temperature of the speed of the sound, example, the speed of the sound in air is 331 meters per second squared at 0 degree temperature and 344 meter per second at 22 degrees. The speeds of sound at particular temperature in various media are listed in table 12.1. You need not memorize the values. What is a sonic boom? When the speed of any object exceeds the speed of the sound, it is said to be traveling at a supersonic speed. Bullets, jets, etc. often travel at a supersonic speed. When a sound producing source moves with the higher speed than the sound, it produces shock waves in the air. These shock waves carry a large amount of energy. The air pressure variation associated with this shock waves produce a very sharp and loud sound called sonic boom. The shock waves produced by a supersonic fighter jet has enough energy to scatter glass or even damage a building. So, children, hope you have understood about this point called sonic booms. Reflection of sound. Sound bounces off a solid and a liquid like a rubber ball bouncing off a wall. Like light, sound gets reflected at the surface of the solid and liquid and also follows the same laws of reflection as you have studied in the earlier classes. The reflection or the direction in which the sound is incident is reflected makes equal angles with the normal to the reflecting surface at the point of incidence, and three are in the same plane. An obstacle of a large size which may be polished or rough is needed for the reflection of the sound waves. Here is an activity for you children. You can see the figure. There is a clock, there is a pipe, two pipes. The clock produces sound, tick tick, and goes into the thing and gets reflected, then comes back to the ear. Speed of sound in different media at 25 degrees centigrade statement. See, these are the different materials and at what speed the sound can travel in them. As you see, aluminium, it is 6420, nickel is 6440, steel is 5960, etc. And you can see as it goes down, the speed of sound also varies. Like you can see, for an example, when you keep a ear on the railway track, you can hear the train traveling about few kilometers away. Whereas by the time it comes to the air, you can know that it travels when the train comes near only we are able to hear the sound through the air. But the same thing which is moving in the iron or steel tracks is much faster, and people tend to check sometimes keeping the ear on the track for where the train is coming. Echo. If we shout or clap near a suitable reflection object such as a tall building or a mountain, we will hear the same sound again a little later. This sound, which we call, is called as an echo. The sensation of sound persists in our brain for an object of 0.1 second. To hear a distinct echo, the time interval between the original sound and the reflected one must be 0.1 second. If we take the speed of sound to be 344 meters per second at a given temperature, say at 22 degrees centigrade in air, the sound must go to the obstacle and reach back to the ear of the listener on the reflection after 0.1 second. Hence, the total distance covered by the sound from the point of generation to the reflecting surface and come back should be at least 344 meters per second. So that is 34.4 meters. Thus, the hearing distinct echoes, the minimum distance of an object to the source should be half of this distance, that is 17.2 meters. This distance will change with the temperature of the air. Echoes may be heard more than once if it is designed well, and multiple reflections can occur. The rolling of the thunder is due to the successive reflections of the sound from a number of reflecting objects such as clouds and land. Also, a good example for echo is the Whispering Gallery and the Gol Gumbaz, Bijapur. You can have, it's so well designed, the globe that is exactly technically designed that 17.2 meters is maintained well at most places. You get multiple echoes in this place. And when you shout at the dome, you get multiple reflections. Reverberation. A sound created in a hall will persist by the repeated reflection by the walls until it is reduced to a value where it is no longer audible. The repeated reflection that results in the persistence of sound is called reverberation. In an auditorium or a big excessive reverberation, it likely undesirable. To reduce this, the walls of the auditorium are generally covered with sound absorbing material so that the reflection doesn't take place. The material can be fiber board, rough board, plasters, etc. These will absorb the sound and will not reflect, so that you will can hear one single sound. This is another example. A person clapping his hands near the echo after 5 seconds. What is the distance of the cliff from the person if the speed of the sound is taken 346 meter per second? So here it's very clear that the sound is traveling at a certain speed, and all you need to do is to calculate the distance traveled by the sound, and by which you can measure the distance. Hence, the distance between the cliff and the person is 730 meters squared. That is equals to 865 meters. This is one way of measuring the distances using sound. Here's a small question. An echo returned in 3 seconds. Please find the distance to the reflecting object. The speed of the sound is considered 342 meter per second. Using multiple reflection of the sound, megaphone or loud hailers, horns, musical instruments such as trumpets and shehnais are all designed to send sound in a particular direction without spreading it all in directions. Soundboard may be placed behind the stage so that the sound after reflecting the soundboard spreads evenly across the hall. A megaphone and a horn is the instruments, a tube followed by a conical opening, and this successfully will guide most of the sound waves from the source in the front direction towards the audience. Stethoscope is an instrument used to listening sounds of the body, chiefly, mainly in the heart or the lungs. In the stethoscope, the sound of the patient heartbeat reaches the doctor by a multiple reflection of the sound inside. Range of sound, what the human can hear, and the range which are beyond. The audible range of the sound of the human beings extend about 20 hertz to 20,000 hertz. That is 20 hertz to 20 kilohertz. Children under the age of 5 and some animals such as dog can hear up to 25 kilohertz. As people grow older, the ear becomes less sensitive to higher noises. Sounds of frequencies below 20 hertz are called infrasonic sound or infrasound. If we could hear infrasound, we could hear the vibrations of a pendulum, just as we hear the vibrations of the wings of a bee. Rhinos communicate using infrasound of frequency as low as 5 hertz. Whales and elephants produce sound in infrasound range. In it is observed some animals get disturbed before earthquakes, so they get a very early warning of the very low or very high frequencies. Earthquakes produce low frequency infrasound before the main shock wave begin, which possibly alert the animals. You see in the night when dogs are barking, they are able to hear some sounds of this range, which we humans cannot hear. Frequencies higher than 20 kilohertz are called ultrasonic sound and ultrasounds. The ultrasound is produced by dolphins, bats, porpoise, etc. to communicate. These moths can hear high frequency squeaks of the bat and know that the bat is flying nearby and are able to escape from the place. Rats also know the play games by using ultrasound. Hearing aid. People with hearing loss may need a hearing aid. A hearing aid is an electronic battery operated device with a microphone. The microphone converts the sound waves to the electrical signals, and these electric signals are amplified by an amplifier. The amplified electrical signal is given to the speaker of the hearing aid. The speaker converts the amplified electrical signal to sound and sends ear for clear hearing. Applications of ultrasound. The ultrasounds are high frequency waves. Ultrasounds are able to travel along well-defined paths, each in the presence of obstacles. Ultrasounds are used extensively in the industries and for the medical purposes. Ultrasound is generally used in cleaning parts where it is very hard to reach. And it is also used in aerospace for after machining, the parts are cleaned. It removes all the grease, dust, etc. Ultrasounds are also used to detect cracks, flaws, and metallic blocks. Metallic components are generally used in construction in big structures. This is called a non-destructive checking of the material without breaking, cutting, or anything. The ultrasound can detect the cracks in the material. Ultrasound is reflected back from the defective locations inside the metal block. The ordinary sound of the longer wavelengths cannot be used for such purpose as it will bend across the corners of the defective location and enter the detector. Ultrasonic waves are made to reflect various parts of the heart, form the image of the heart. The unique thing is called echocardiography. The ultrasound scanner is also an instrument which uses ultrasonic waves for getting images of the internal organs of the body. A doctor may image the patient's organs such as liver, gallbladder, uterus, kidney, and etc. This helps to detect a lot of things inside the body. Similarly, like abnormalities such as stones, gallbladder, kidney or tumors and different organs. In this technique, the ultrasonic waves travels through the tissues of the body and get reflected from a region where there is a change of tissue density. These waves are then converted into electrical signals that are used by to generate the images of the organ. These images are then displayed on a monitor or printed on a film. This technique is also called ultrasonography. Ultrasonography is also used for examination of the fetus during the pregnancy to detect congenital defects and growth abnormalities. Ultrasound may be deployed to break small stones formed in the kidneys into a fine grain. These grains later get flushed out with the urine. Sonar. Sonar stands out for sound navigation and ranging. Sonar is a device that uses ultrasonic waves to measure the distance, the direction, and the speed of the underwater objects. How does the sonar work? Sonar consists of a transmitter and a detector and is installed in a boat or a ship as shown in the following. The boat, the water surface, the detector and transmitter, and the seabed. So automatically these waves get reflected and they keep measuring the depth of the bottom. Ultrasound sent by a transmitter and received by a detector. The transmitter produces and transmits the ultrasonic waves, and the waves travel through the water, strike the seabed, etc. So then it is easy to know about the total distance 2D traveled by the ultrasound. So 2D can be divided and you can know the depth. Here is an example of the calculations. Just go through the picture which clearly explains you the calculation and also the solution and how the seabed from the ship is 2618 meters is the result of the calculation. Now let's move to the structure of a human ear. How do we hear? We are able to hear with the help of an extremely sensitive device called the ear. It allows us to convert pressure variations in air with audible frequencies into the electric signals that travel to the brain via the auditory nerve. The auditory nerve aspect of the human ear is discussed below. You can see on the right the entry, external canal, and you can see other parts where it receives the vibration and converts into a electrical wave. to reach the brain. The ultrasound is emitted by bat and is reflected back by the prey or an obstacle. The outer ear is called pinna. It collects the sound from the surroundings, and the collected sound passes through the auditory canal. At the end of the auditory canal, there is a thin membrane called eardrum or tympanic membrane. When the compression of the medium reaches the eardrum and presses on the eardrum, it forces the eardrum inward. Similarly, the eardrum moves outward and refractions are caused. So it's the typical thing which we have been talking. There are three bones called hammer, anvil, and stirrup. In the middle here transmits the amplified pressure received from the stone from the outside. The inner ear pressure variations are turned into electrical signals by the cochlea. These electrical signals are sent to the brain via auditory nerve, and then brain interprets them as the sound. Last summary of what we have learned today. Sound is produced by due to the vibration of different objects. Let me come back again. Sound is produced due to vibration of different objects. Sound waves travels as longitudinal wave through a material medium. Sound travels as a successive compressions and refractions in a medium. The sound propagation is the energy of the sound that travels and not the particles of the medium. Sound cannot travel in the vacuum. The change in the density of one maximum value to the minimum value and again to the maximum value makes it a complete oscillation or a cycle. The distance between the two consecutive compressions or two consecutive refractions is called a wavelength. The time taken by a wave to complete one complete oscillation of the density or pressure of the medium is called a time period T. The number of complete oscillations per minute is called frequency, which is also called cycles per second or minute. For hearing a distinct sound, the time interval between the original sound and the reflected one must be at least 1.1 second. The persistence of sound in an auditorium is the result of repeated reflections of sound and is called reverberation. Sorry. Sound properties such as pitch, loudness, quality are determined by the corresponding wave properties. Loudness is a psychological response of the ear to the intensity of the sound. The amount of sound energy passing through each second through unit area is called the intensity of sound. Audible range of hearing for average human beings is in the frequency range of 20 Hertz to 20 kilohertz. The sound waves with frequencies below the audible range are termed infrasonic, and those above the audible range are ultrasonic. So below 20 Hertz is infrasonic and above 20 kilohertz is called ultrasonic. The ultrasonics has got many applications in the modern world. The ultrasound has been used in many medical and industrial applications. The sonar technique is used to determine the depth of the sea and to locate underwater hills, valleys, submarines, icebergs, sunken ships, etc. Right, children, here are the set of exercises for you. Please go through, read this, and please prepare them or answer them at your place and also you can discuss among your friends, and please complete all the exercises and which will help you in understanding the whole chapter. Right, children? Now we come to the end of the chapter. Please complete exercises at home. See you all in the next chapter. Thank you. Goodbye.